Yeah, so a very good afternoon, everyone. I am Kshitij Anand. I am a recent graduate from IT Kharagpur. I completed my dual degree in aerospace engineering. I hold a minor in computer science and engineering and a minor in artificial intelligence and its applications. For the past year, I had been associated with MN Farooqui Innovation Center. We were basically mostly working on robotics, and today we are here to conduct a UAV workshop in a remote mode. This workshop will be in 2 days. First one will the day one will be related to hardware. We'll be discussing about different types of UAVs. How do we design a UAV? What are the component selections? And if you look right behind me, there is a full-scale RC model for demonstration purposes. How we can build one, what to what things to keep on your mind, and how to make it accessible. Our focus today for this workshop has been that we find that a lot of drone accessories and a lot of drone equipment is super costly if you try to build it from a kit. But however, if you try to do it from scratch, what you can do is you can really make it in a much cheaper way, provided you understand the basics of how an RC aircraft works and what are the different components that go into it. So there will be a few sections. So we'll be talking about what is an UAV. There will be different types of UAVs. What are the different three primary methods of lift generation? And then we are going to look at some of the classic examples and compare how, two different products in the same UAV line have different demands and have different requirements. How do we look at UAVs from not just a research perspective, but also from a market product perspective? And then we look at the design choices. How do we design a UAV from scratch? How do we go about doing so? And what things should we keep in mind, and what are the different parts of the UAV that we focus on one by one? So I'm going to stop in between, like after the types of UAV section is complete, and I'm going to stop every time after each subsection of the design choices. That is, I'm going to stop after wingspan, after fuselage. If you have any doubts, you can ask it there and then. And in the end, for half an hour or so, I'll switch over to my mobile phone, and we are going to see an RC plane up close, how I made it, and what are the tips that I would give to a person who is making an RC aircraft for the first time. So let's begin. So what is a UAV? So there is no strict definition. However, more or less, one of the dictionary definitions picked up from uh, Google is that it's an unmanned aerial vehicle is defined as a powered aerial vehicle that does not carry a human operator. It uses aerodynamic forces to provide vehicle lift, and it can fly autonomously or pilotly remote. It can be it can be piloted remotely, and can be expendable or recoverable. It does not necessarily have to be so, and can carry a lethal or non-lethal payload. So basically, if you look at what three aspects make up a UAV, is how are you going to produce a lift? How are you going to keep the vehicle up in the air without its frame breaking down? That's the most important part, because not all parts of the frame are going to produce lift. Only the wings are going to produce lift. The empennage, that is the tail section, is going to produce lift. So how do you keep the rest of the please do not make any requests to record. This meeting is being recorded and it will be put on YouTube. Okay, so moving on, so today we'll look at the frame part, the hardware part, how do you make a UAV? And tomorrow we'll be looking at manual control, autonomous control, how do you control the motor? And then it's up to you what payload you want to carry. So these are the three aspects which determine how your whole UAV is going to work. So UAV is not just a single, um, what do you say? It's not a single device. It's not a single entity. It's a whole system. When I talk about a UAV cannot be a standalone system. Why do you ask so? Because UAVs cannot be controlled using wires. Like, as in, you have to have remote control with them. They are flying quite far away from you, so you need to have a whole UAV system in place which is going to There is going to be the aircraft itself, then there is going to be a manual control system, then there is going to be an observer, then there is going to be a control system. So we'll talk about all of this. So what are the types of UAVs? So there are a lot of bases of classifying UAVs. Like there are multiple trivial bases, as in I call them trivial because they generally don't make an impact on the specific physics related to the UAV. For example, how many drones the UAV is having, also how many motors the UAV is having. Pardon me for the mistake. How many motors the UAV is having, how many propellers it is having, or what payload it is carrying. There are multiple bases you can classify UAVs on, but the most important basis on which you classify UAVs is the method of lift generation. And in today's discussion, we are going to talk about three methods. I'm pretty sure that you are aware of the first two methods, that is fixed wing and rotor wing. And the third method, which is the flapping wings, is a relatively recently developing field. I myself have done my bachelor's thesis, my master's thesis, and most of my research is centered on flapping wings. But be our like be sure that if you do not understand fixed wings and rotor wings in detail properly, you'll not be able to do a lot of work on flapping wings. So if you want to start your journey into RC aircrafts or into research in aerodynamics and flight controls, you need to get yourself acquainted with fixed wing aircrafts and rotor wing aircrafts. And those are the basics. Like, they are simpler to understand. Like, it's not simple as in, they're simpler to understand than flapping wings, to put it more precisely. So the fixed wing aircrafts, as you can see, they have fixed wings. Their wings do not move. And if you look close enough, so this is a zipline UAV that I have taken for example. It's dropping a payload, and you can see there are two sets of propellers here, which are run by coaxial motors, and there is a controlling tail at the end. So this is how a fixed wing UAV looks like. So most of this lift, like most of what, not most of it, all of its lift comes from these fixed wings. Then we talk about this rotorcraft UAV, which is DJI. I guess everyone knows about DJI. And if you haven't watched the latest release video of DJI Inspire 3, I seriously suggest you to go and watch it. Even for a non-scientific person who is not into engineering and science, if you really want to inspire yourself with what capabilities a UAV with 4 propellers and 4 motors can achieve with a high resolution camera on board, you'll be amazed. So I guess I strongly recommend that all of you go and see the promo video released by DJI, which shows Inspire 3 in action. And finally, we talk about flapper drones. So this was a flapper drone I had access to when I was doing my internship in TU Munich last summer. So this is the only drone right now available commercially in the market. The company itself is called Flapper Drones, and it was basically, it's an entrepreneurial company which started about like in the year 2015 in MAV lab in TU Delft. And I had an opportunity to sit in one of the webinars and personally talk to the founders of this company. His name is Matej. So they have developed these drones primarily for, not for some surveillance or military applications, but right now these drones are mostly for show and for recreational purposes. Why do I tell you so? Because though we have been able to make flapping wing MAVs, either they have been of very smaller scale, or if we have been able to make bigger ones like ornithocopters or mimicking birds, it's very difficult to control them. Why is it so? We'll understand briefly when we talk about flapping wing MAVs or UAVs later on. Also, if you're confused what MAVs are micro aerial vehicles, UAVs are unmanned aerial vehicles, and when I say FWMAVs, they are flapping wing micro aerial vehicles. So next, we talk about fixed wing UAVs. So I guess not all of you are from an aerospace mechanical background. Can I have I'll just create a quick poll to understand the real time data of who am I, how many people I'm dealing with. So just answer this quick poll. Yeah, can you guys see a poll on your screens? I guess you can. And can you just quickly answer this question for me so that I have an idea of what kind of audience I'm dealing with? Okay, so we have an almost 50-50 response. So I'm going to end this poll, and I'm going to, I cannot cover, obviously I cannot cover all of flight mechanics and dynamics in very depth in this video, but I'm going to give you the gist of what all is important to understand what we are going to discuss further ahead. So first of all, as you saw in fixed wing UAVs, the wings are stationary. When I mean stationary, all of the talking that I do regarding moving parts and stationary parts will be from the body frame. Body frame is centered on the basically on the aircraft itself. So basically, if I have an aircraft and I look at it from the top, then I guess you can see I'm sketching something on the screen. So if this is the, the fuselage of the aircraft, this is the tail. I am looking at the top view, and these are the wings. Then basically what do we have is we have this body frame axis fixed at the center of gravity. The origin is at center of gravity. We have one axis going this side, one axis going this side, and one axis going below. So if you look at the, so basically this is how we take the reference frame of the aircraft, and this is called the body fixed frame. So whatever moving or stationary I'm talking about will be from the respect of this body fixed frame. So what are the four primary forces that a fixed wing UAV experiences, or any UAV experiences, are lift, thrust, drag, and weight. So if you look at this diagram, basically what is happening, we are considering that an aircraft is simply taking a turn and is not moving sideways, and it's simply taking a turn in the vertical plane. So what are the forces that are going to be acting on it? So basically there is going to be lift, there is going to be drag, there is going to be its own weight, and there is going to be the thrust. Now what is happening, you need to understand something called the velocity vector or the free stream velocity vector. Again, what happens is the air around us, we assume that it's not moving right now. It's the aircraft which is moving. But if you were a pilot, driving the aircraft or flying the aircraft, you would see the air moving towards you. So so from your perspective, it's like from the driver's perspective, it's called the free stream velocity vector, and from the ground perspective or from the air perspective, it's called the flight path velocity vector or velocity vector. So as you can see, this is the flight path, and then this is the velocity vector of the aircraft, which is obviously tangential to the flight path. Velocities are always tangential to the path. And then this is the reference line of the fuselage. Okay. So the thrust again, so there will be some engine here. The engine need not be placed exactly horizontally to the wings, or in line with the fuselage. They are many a times offset by some angle. To study about this in detail, you would have to study flight dynamics and engine installment in detail. But yeah, know that thrust is not exactly aligned with the fuselage reference line. And yeah, and then we have, there is an angle between lift and weight and drag. So basically what I wanted to discuss here that is more important is in this diagram right here, you see that the lift and weight are at the same points. So this is just a simple free body diagram to make you understand the difference in, what do you say, the difference in different forces. However, what happens when you have an airfoil, I'll just use a sketch that is better. Yeah. So when you have an airfoil, it produces and it's moving in this direction. So it will encounter a free stream velocity in this direction. So it is going to produce lift. And this lift is like all of you have known that if there is a continuous lift distribution, you can approximate it as a single force on one point by averaging it over the whole length. So we can call that point where that is the point where lift is being applied. This point is called aerodynamic center or the center of pressure. And for our RC purposes, I am again telling this in very detail. For the people who are studied aerospace engineering, they know that this is not like a solid fact rock, like a rock solid fact. But for just for RC purposes, keep in mind that your center of pressure is more or less going to be around the place where your airfoil is the thickest. We are going to discuss what kinds of airfoils we are going to use, but if we were to make an approximation, because when you are making an RC aircraft, you are not making something like, it's not something NASA has demanded. So you are not going to, go into very high level detail of doing CFD analysis and stuff like that. So you are going to make some approximations, and you can approximate that this CP is going to be roughly at the point where your airfoil is having the maximum thickness. And because it is at that point, it is around that point or around that line of points where the lift is maximum, and more or less the average lift vector will be pointing out from that place. What we try to do while making an RC aircraft is we try to keep the CG ahead of this. Okay. And why is it that? Is that the case? Because what is going to happen is you have a tail in the aircraft and you have the main wing in the aircraft. So if you want to go into much more depth about this, you need to study about stabilities. So stability is basically determined by the relative locations of center of pressure and center of gravity. These are more or less along the fuselage reference lines. And we try that the CG should be kept basically aft of the center of pressure, and so that there is at least positive static stability. What does positive static stability mean? That if you are inclining your aircraft nose up to go up to climb up in the air, there should be a natural tendency for the aircraft to come down. You should have to apply force to you should have to apply force to keep it nose up. If you do not need to do that, what is going to happen? The moment you're applying force to put it nose up and it does not have a tendency to come back down, it will keep increasing its pitch, and that will lead to stall. Basically, we'll discuss stall later on. Stall is basically you simply can't keep on pitching your airfoil all the way up and expect the aircraft to fly. After a certain angle of attack, after by a certain angle you have pitched it up, the aircraft is simply going to lose lift and it is going to fall down. So we want that we apply as much force to keep it nose up in a certain position, and then when we release our controls, the aircraft should have a natural tendency to come back down. So how do these airfoils generate lift? Again, I have kept this slide because I knew that more or less people, there will be people from diverse backgrounds. So I guess everyone has studied Bernoulli's theorem in their high school or for JEE purposes, and what do I say? And they know more or less how lift is generated around an airfoil. However, let me be like very, very straightforward that that's a very naive idea of understanding how lift is generated, although it works just for these cases because it's derived from potential theory. So it works for these cases, it works for RC aircraft, so we can use all those formulations and all. But if you really want to develop an understanding of how lift is generated using airfoils, you should get into depth of how do you calculate circulation and how do you identify the velocity field around an aircraft if you want to go into depth. However, just for our RC purposes, you should know that basically this is the upper surface of the airfoil and this is the lower surface of the airfoil. this piece should be streamlined to minimize drag. So drag is the force which acts in this direction because it is stopping flow in this area from moving forward. It's asking it to deviate its path. And that is why the flow will create resistive force, and that force is going to be drag. And to minimize this drag, this should have smooth contours and no sharp points or blunt force or blunt faces. That is going to increase drag. So to make it smooth, we keep a rounded tip and we introduce more curvature on the top surface and lesser curvature on the bottom surface. This basically leads to more deflection of the flow on the upper part and lesser deflection on the flow of the lower part. However, the net deflection for the overall flow is somewhere downwards, and that is why the flow on the airfoil produces a force upwards. So that produces lift. And there are different ways of understanding lift. um, you can basically subtract the free stream velocity vector from all the vectors, and you can understand that basically what you can see is that if you just look at, so if you were just, what do I say, if you were just sitting on the ground and you're observing, if you're sitting on the aircraft and observing it, this is how the flow would basically look like to you, because that is how the flow is moving around the airfoil. And if you were, sitting on that frame, then you will see that this circulative effect is coming into place, and you can calculate lift using circulation. So again, this topic is beyond the scope of this workshop because our focus is to jump to the practical part as quickly as we can. And yeah, next we come, how do you design RC aircrafts? So um, I have two examples here. So the first one is Zipline Platform 1, and the second one is General Atomics MQ-9A Raptor aircraft or Raptor UAV. So both of these UAVs have pretty different usages. They have pretty different requirements. Zipline is dropping parcels across Rwanda in Africa, and General Atomics MQ-9A Raptor is a military surveillance UAV. So both of them are fixed wing aircrafts, but because they serve very different purposes, their requirements are very different. Now, if you look at this slide, the title, basically the subtitle says, what does a fixed wing UAV VOC look like? So VOC is nothing else, but it's called, I probably left it blank because I wanted to highlight it. Most of you do not come across this term. So this term is basically called voice of customer. So when you are making a product, when you are working in industry, so when you're working in the industry, you take requirements from your customer, that what performance do you want, and that list of requirements is called voice of customer. And it is not necessary that you're going to fulfill everything. When you take requirements from your customer or when you take requirements from yourself, you also need to prioritize which feature you want. What is more important? Do you want it to spend more time in the air? Do you want it to carry more payload? Do you want it to go further? What is more important? Because while designing an aircraft, you will see that if you want to carry more payload, it may not be able to fly longer. So you will have to create a trade-off somewhere, and that is why an importance between these requirements and like a relative importance of these requirements is extremely necessary. So if you look at the requirements, so the cruise speed of the zipline UAV is roughly 101 kilometers per hour. The level flight altitude is 80 to 120 meters. AGL or AMSL, it basically AGL is above ground level and AMSL is above mean sea level. So it depends upon where you are flying, and the altitude can be described in that way. Its endurance is 2 hours. The maximum payload it can carry is 1.8 kilograms. So when I mention payload, payload is just the thing that you are carrying. So the term payload is used like it does not account for the weight of the aircraft, the weight of the frame, the weight of the propellers. Nothing about the aircraft, just the item it is supposed to deliver. Let's say it's an Amazon packet. So if an Amazon packet was aboard a drone, it was supposed to, shed it off somewhere. That is going to be the payload. The range is, so like for example, when you are traveling on an aircraft, all the humans and the food and the luggage is the payload. Okay. The range is 300 kilometers. However, because of factor of safety, it's limited to 80 kilometers per operation. They change the battery after every 80 kilometers. I also recommend that you go on YouTube and see how the zipline functions as a company, like how drones come in, their batteries are replaced. So that gives you a really nice idea that if you were to make UAVs that were on a continuous operational run, how should you design them? How should the structure be designed so that they can be taken apart quickly and a new battery can be installed while the older battery goes to charge. Then we talk about now next aircraft where we have as example is the General Atomics MQ-9A aircraft. So its maximum speed is 463 kilometers per hour. So you see now, when they sell this aircraft in the market, they market it based on cruise speed because it is just supposed to make a boring flight, a flat level, constant speed boring flight. We are not in a hurry. We are scheduling departures. We are scheduling arrivals. Everything is organized. It's not fighting another aircraft. We don't want it to fly on maximum speed. We want to flight at a comfortable speed. That is why we'll sell the point of cruise speed. But when you want to sell a drone to a military person, or to when a customer is a military faction, then you got to tell them that it can fly this fast. It can intercept someone traveling this fast. However, its cruise speed might just as well be around 200 300 kilometers per hour. Then there is something called the service ceiling. Service ceiling is basically the maximum altitude your aircraft can climb to, because as you climb altitude, the density of air gets lesser and lesser. And basically, when your propeller spin through the air backwards and generate thrust, if that density reduces, if the density of the working fluid reduces, your thrust is also going to reduce. And you're not going to keep up with the drag. Hence, what is going to happen is you are going to fall down. So there is this maximum ceiling where you can take the aircraft to. Then there is endurance. They are marketing fixed wing UAVs will always have endurance on their marketing specifications, because fixed wing UAVs are really good at endurance, and we'll just know about that in a few within a few slides. That why endurance is so prime in fixed wing UAVs, and the rest of the other two UAV classes do really bad on endurance. Then there is the maximum payload it can carry and the range, obviously the range it has. Next, we talk about rotor wing UAVs. So these have spinning propellers or blades which provide thrust. And if you want to move it around, there are two ways of doing so. So what you can do is, if let's say you wanted this aircraft to tilt this way, then you can simply increase the thrust on these two and reduce the thrust on these two, and the rotorcraft will tilt. If you wanted to make it move like this, then you could simply change the rotational speeds to make it yaw. So here, the movement is all done using changing the speed of the motors. The other way of tilting an aircraft is using tilt rotors itself. So here the motors are itself mounted on a tilted duct. So basically, this aircraft has a small fan at the back. You don't see it. I worked on this aircraft itself in my tax internship after my third year. So this is a Navigate. It's built in Canada, and it's being used as an assistant to first responder teams in their fire safety department. So basically, this has a small fan attached at the back, which basically controls its pitch going up and down. And then these two rotors can tilt on their axis. And it can, provide thrust vectoring, and in which direction do you want to go. These two vectors, like these two. So these are the two methods of thrust vectoring and moving the aircraft around. It's much easier to control, like as you can understand, it's much easier to control this rotor wing UAVs and in comparison to fixed wing UAVs. is because fixed wing UAVs have a lot of control surfaces. We are going to talk about control surfaces in a short while when we start discussing how to make a UAV, how to make a fixed wing RC UAV. So if you look at these fixed wing UAVs, you are going to see that to make it tilt, there are these ailerons here which are blended into the wing right now. You don't see them, but they go up and this goes down to make it tilt in one direction. Then these are V-tail rudders, then which also act as an elevator. So, and these are also, this is a plane rudder. So there are a lot of control surfaces here at play, and you don't really have, the control over the motor. Like, it takes time for you to control a fixed wing UAV. However, it's much easier to, the response time is very critical in fixed wing UAVs. However, you can easily control a rotor wing UAV. The endurance is very poor. Why do you ask? Why do you say so? Because you see, the motors themselves are, acting to, the motors themselves are also responsible for, taking up the weight of the rest of the aircraft. If you looked at fixed wing UAVs, the motor is only giving a thrust in this direction, which is countering the drag in this direction. Now the drag forces are much, much lesser than the lift forces, the required lift forces. So the lift forces are provided by these fixed wings, right? So the motor only has to provide as much thrust to counter the drag encountered by the aircraft. However, in rotor wing UAVs, the motors also have to, like, the motors not only just provide lift, they have to also encounter the weight. So you have to go beyond the weight, and whatever is beyond the weight is going to be your lift. However, again, I told you it's much more easier to control a rotor wing UAV, so it has better agility. So if you wanted to, make a flip turn, it's much more easier for a quadcopter to do it rather than a fixed wing. A fixed wing aircraft can't simply make a flip turn, like, not without going forward and making a turn. However, a rotor wing aircraft can, just stay in one position and make a flip turn. So it's much more agile as compared to a fixed wing UAV. So these are the components of, rotor wing UAVs. It is going to have 4, 6, or 8 motors. They'll have propellers. You'll have a frame. Carbon fiber frames are available in abundance today, like these days, and they are super lightweight. However, you can go with things like balsa wood or Depron foam. We'll talk about all of that in detail later. So what are the other things that are present there? There has to be a computer on board, which, there has to be a brain on board basically. There can be a camera, there has to be a, controller for motors. You need to know the location of your aircraft. You also need to have different sensors, to control the movement of your aircraft. Moving forward, um, rotor wing UAVs, how, like, basically they use spinning propellers to produce thrust, right? So basically what is happening is, if you want to understand this in detail, I have not taken up this theoretical part because it's not our focus. However, if you are, a junior student or someone who wants to start foraying into aerodynamics and understand really how propellers work, you need to understand these three theories really nicely. So the blade element theory basically tells you how you can, break down a propeller into small slices. You calculate the lift on each slice, and you take the lift average of the whole revolution, and then you sum it over the whole propeller. You get the thrust produced by the propeller at a certain revolutionary speed. Okay. However, there is a problem that how do you calculate or how do you determine what is the incoming velocity or the induced velocity on the propeller? That there are some assumptions that the blade element theory makes. However, those assumptions do not provide very accurate results. They provide workable results, but if you really want accurate results, you can, study momentum theory, which shows that basically momentum theory is going to account for a propeller as a thin disk, and then it is going to give you the relations between induced velocity and the velocity after that. And then you combine the blade element theory and the momentum theory to and that results in blade element momentum theory, which is the most accurate description of like the most accurate description of how a propeller produces thrust. And it's going to give you the best results if you are, if you want to analytically determine how much thrust a propeller is providing. However, if you are working with RC aircrafts, you do not need to bust your head so much about how much thrust your propellers are producing. But in case you wanted to design propellers, like for example, some new propellers have come up, like the toroidal propellers, which are very efficient. They do not produce as much noise, but it's difficult to manufacture them. If you want to just take a note, I'll just put it down. If you can go and look up toroidal propellers. If you're just curious enough, these are new kinds of propellers, and you can just have a look at them. So again, comparison of two classic examples of rotor wing UAVs. So how does a rotor wing UAV VOC look like? Again, the most important setting here is going to be endurance. Okay, there it was the speed at which, for fixed wing UAVs, it's the speed at which you are flying or the maximum speed at which you can combat. But for uh, rotor wing drones, it is the endurance, because again, I told you, motors are doing the work of keeping the whole aircraft in the air. They're encountering the weight. So they are consuming more energy. In fixed wing UAVs, motors are only encountering or only working against drag. So they are consuming much less energy. The lift is being produced by the wings. Right. So here the endurance is most important for rotor wing aircrafts, and that is why that is like the most important the most important factor. Then what is the maximum takeoff weight? Here we do not talk about range as such, because the drone can really travel as far as the battery, what do you say, again, as much as the battery goes. But the most important part here is that we don't, like, fixed wing drones don't fly for really long ranges. They are for like short range applications, but they are much more agile. They can go into smaller spaces. They can take off and land in smaller spaces. So if you have space restrictions, rotor wing UAV is the thing you're looking for. Okay. Finally, we talk about flapping wing UAVs. So basically, here, this is a prototype of the flapping wing MAV that I have developed during my research. So these wings go up and down, and then basically there is another motion which makes the wings move. So basically the flapping wings, I could just have a, I could just use something to show you a demo. Yeah. So this is, let's say this is one of the wings. So that's like how basically how insects flap their wings. So if this is the place where the wing is attached to the body, then this motion is called heaving motion, this motion is called stroking motion, and this motion is called pitching motion. So a combination of these three motions, stroking, heaving, and pitching, generates lift. It's a very, very involved and complex aerodynamical phenomena. Um, uh, you can, like, if you are a student in aerospace engineering who is into aerodynamics, or someone in mathematics studying fluid dynamics, or someone in mechanical engineering working on fluid dynamics, this is a really, really active area of research. And if you're looking for a research topic to work on your project, because after this summer, people are going to have PTPs and MTPs. This is one of the most interesting topics you can work on. There are a lot of different angles you can work on. The aerodynamics is still not understood analytically. The dynamics is also approximated. So it's an active area of research. The lift generation here is primarily due to unsteady phenomena. What is unsteady phenomena to the people who are not from an aerospace mechanical background? So when a fluid is flowing, or there is movement in the flow field, We can call it steady or unsteady. Steady is when the flow field does not change with time, and unsteady is when the flow field is changing with time. So when you have like fixed wing UAVs, once it starts traveling at a constant speed, right? So the flow field roughly looks the similar all the time. So we can call it an unsteady phenomenon. We can call it a steady phenomenon. Similarly, the rotor wing, the rotor blades, although they are moving with time, but the flow field around the blades is going to be roughly similar most of the time. So it can be very well approximated with a steady phenomenon. However, here very complex 3D motions are going on, and the unsteady phenomenon is highly predominant. And we are like, as human race, we are really lagging in understanding unsteady phenomena. So like, these are not my words. Like, I'm a very newbie researcher, but these are the words of very prominent scientists writing the research papers. Almost everyone who writes a good article writes that as a human race, we are lacking a good understanding of unsteady aerodynamics. So yeah, so these are some of the, I have just put in this slide. I am not going to discuss this, but in case you are someone looking to start, a research project, or wanting to start in this direction, these are the concepts that you need to learn in unsteady aerodynamics before working on flapping wing microaerial vehicles or flapping wing UAVs. The importance, the more important fact is that, just to make the rest of the people aware and everyone aware, where are we with respect to flapping wing MFVs? I mean, they're difficult to understand, but are we at level 0 or square 1? No, we are not. So if you look at the first UAV or MAV, let's say, so this is RoboFly. Okay, so let me just zoom in. I think this is a much clearer picture. Yeah. So this was developed in 2018 in this was developed in 2018 in the University of Washington, Seattle. And as you can see, these are the tiny wings it has got. These are some triboelectric actuators. And these are the copper wires that you are seeing. These copper wires are powering this flapping wing MAV. So, and this coin here has been showed as to, to make you understand the relative sizing of, just give me a second. Yeah, sorry for the interruption. So, so this coin has been shown here so that you can see the relative size of this aircraft, like of this UAV, MAV, with respect to the coin. They are kept side by side just for size comparisons. So this is how small. So this is a 1 cent nickel coin, a dollar nickel coin. Then this is RoboBee. This is only slightly bigger than RoboFly. Slightly bigger as in just of the same size. It was developed at Harvard. Again, it uses triboelectric actuators. And then you have this flapper drone, which is again, so this is only 15 centimeters. So, and here the movement, if you can see, we are using like gear systems, and the control is made through servo motors. So when you go really small, you do not have the options to use servo motors. You only have the options to use triboelectric actuation. That is like, now this thing goes much more closer to understanding, biological skeletons and how our muscles work. So triboelectric actuation is very similar to how our muscles work, and we are trying to make the wings flap based on such actuation. Yeah, so we are moving on to the next section of our design choices. I'll break for 5 minutes or so, or let's say 2 minutes. And if anyone has a question, then they can put it down in the chat, or in the, if they don't want everyone to see it, you can put it in the Q&A. I'll answer them. No one? Okay. Um, Now coming to the juice of the presentation, we talk about how do we, like we finally get into the nitty gritty details of how do we build an RC aircraft. So what are the design choices that we have to make is, first of all, we need to know what it is going to do and how much weight it is going to carry. Okay. So today I'll not be doing an exact full on calculation. Today I'll be going over the whole process. Tomorrow, when we cover the last part of control, that is ESCs, then I'll take you through a sample sizing calculation. So today we'll just look at the overview. So first of all, we need to find out what takeoff weight it is going to have. For example, the whole frame, the electronics and the payload. Then for how long do you want it to fly? That is going to affect how big of a battery do you want it to take. Range, again, how far do you want it to fly? That also depends upon like how much battery you're going to need. What features do you want? Do you want to drop a payload? Do you want to do video recording? Do you want it to carry missiles to shoot someone? However, we'll not be talking in that direction. We want aerospace engineering to be put to good uses. And what capabilities do you want? Do you want do you want it to land it on water? Do you want to land it on the ground? Or do you just want to, drop it somewhere? And there are some symbols that I would like you to know as we go into the discussion further. So this symbol rho means density of air. The symbol V is free stream velocity or the cruise speed of the RCS craft for our purposes in this workshop. C is the chord length. Mu is the dynamic viscosity of air or of the surrounding fluids. And there is this critical number in fluid dynamics called Reynolds number, which is a ratio of, basically inertial forces to viscous forces in the flow field. Okay. And this determines the flow field characteristics completely for our purposes, for specifically for subsonic flights. So Reynolds number is going to determine the characteristics of the flow field to a large extent. All of the forces, force coefficients, moment coefficients we see are going to be valid for a given Reynolds number. Okay. And Reynolds number is dependent upon four things. The density. Density basically talks about the inertia of the fluid. The C is the characteristic length or the chord length. V is the free stream velocity, and mu is the dynamic viscosity of the fluid. So first of all, what kind of wing do we want? How do we decide what wing do we want? So mind you that I had already mentioned in the form and in the email also that our studies related to design choices and the making the RC aircraft actually will be centered on a fixed wing UAV for this workshop. Because this is an introductory workshop, we are focusing on fixed wing UAVs. Okay. We decided not to focus on rotor wing UAVs because rotor wing UAVs are very simple to make. You just need to get an X frame, strap on 4 motors. You need to get an autopilot downloaded and you're good to go. You don't need to understand how control surfaces work. You don't need to understand anything else. Making an X, like making a quad rotor is as easy as making an RC car. So fixed wing UAVs are really difficult to make if you don't understand how each of the control surfaces contribute to its movement. So here we have two kinds of aircrafts. One is a conventional fixed wing RC aircraft and another one is a blended wing body aircraft. By the way, this is not a life-size aircraft if you're wondering. This is a experimental RC drone. The only difference is, yes, this is actually being made by NASA because NASA is studying the properties of blended wing body aircraft. And this experimental aircraft is called X-48B. Again, if you are an aerospace enthusiast and love watching at aircraft, you should go and watch the YouTube video where NASA has posted it. Like it has published its trial run of X-48B. So moving on, so every wing, the cross section of a wing is called an airfoil or airfoil shape, And basically, what are the things like how do so you see the airfoil does not have a very straightforward geometry. You need several parameters to determine the geometry of your airfoil, and then how do each of these parameters or which of these parameters affect the lift and drag that your airfoil are producing. Okay, and then we will discuss in what cases do you need a certain type of airfoil and in what cases do you need another type of airfoil. So when we look at this airfoil shape, so you can see that basically this is the airfoil outer contour. Okay, so the leading edge radius is important. This is what decides how blunt or sharp it is going to be at the leading edge. So basically this is called the mean camber line. So before I talk about this, I want to tell you two things, is that an airfoil can be shaped like this and an airfoil can be shaped like this. So this is almost symmetrical along its chord. So the line joining the leading edge and the trailing edge is like basically called the chord. So it is symmetrical on the upper half and the lower half. And then this is the leading edge. Let's say this is the trailing edge. This is the chord line. So now this is not symmetrical. So this is asymmetrical airfoil. This is so there is a symmetrical airfoil and this is an asymmetrical airfoil. So what you are going to notice is that the camber is basically tells you how asymmetrical, the mean camber line tells you how asymmetrical the airfoil is. Then there is the thickness of the airfoil, the chord length of the airfoil, and this angle, the angle of attack, is very important to understand. The angle of attack is basically the angle between the chord and the oncoming free stream velocity. Okay, or basically your flight path vector. And this is sometimes they might have an angle between them, but for our RC purposes, we'll assume that the flight path vector and oncoming free stream velocity have roughly the same angle. So next, yeah, we talk about the thickness distribution. So as I was telling ahead, again, this is not a scientific fact, but this is a thumb rule that when you are working with RC aircrafts, your CP is roughly going to lie around the line of maximum thickness. This is a thumb rule, not a scientific fact. It can, if you have a, like basically your center of pressure or aerodynamic center is going to be different for at different sections of the wing. It is going to be a function of where the camber, how the camber varies over the chord and how the thickness varies over the chord. Okay, yeah. Why am I saying again and again that this is a thumb rule for RC aircrafts is because when you are working with RC aircrafts, you make really simple airfoils. You do not construct very complex airfoils because you are making it with like simple materials. You can obviously use very high-end materials when you are further into the research or making an advanced product. Then obviously you'll have to know an in-depth, have to have an in-depth knowledge of the airfoil characteristics. However, because this workshop is aimed at junior students and the people who want to get started with RC aircrafts, we make simpler airfoils, which we'll discuss just in a short while. And these are the thumb rules that you need to note down. So how does the pressure distribution look like around a typical airfoil is, as you can see that this is the pressure is below atmospheric, like the pressure is below the atmospheric value, the pressure is above the atmospheric. So what is happening is basically because this is below, a lift force is being generated here, a force is being generated pulling down, right? So this is a suction force, this is the upward lifting force. So net force is on the top and the net force in the drag direction is here. So we have two forces, one is drag and one is lift if we have the free stream velocity coming in this direction. Drag is always in the direction of the free stream velocity. Lift is always perpendicular to the free stream velocity direction. Okay. That's how lift and drag forces are defined in the first place. What shape and size? So which airfoils to use? Okay. So this is a family of airfoils that most of the RC aircrafts people, like the people working with RC aircrafts or hobbyists, are using. Why? Because they are much easier to make. You can simply stack, you can simply stack, basically I'll show you. You can simply stack different foam boards on top of each other and make an airfoil. You don't need to, introduce curves and bends to make an airfoil. It's really easy to make a KFM family of airfoils. And there are roughly nine airfoils, sorry. And I'll attach this slide with the YouTube video that I'll put on. However, you can make a simple Google search and you'll find all these airfoils. So for example, every airfoil has its own quality and you have to go through every airfoil's like description before deciding on what kind of airfoil to use. Okay. So for example, this is very mild stall, very stable, very mild stall. Okay. Very stable, moderate lift, simple build. Okay. But then it does not have a good lift. It has moderate lift. If you want higher lift, then you go with this. If you want more stabler lift as in the stall happens at a later angle, you go with KFM2. So that is how you make a choice of the airfoils that you are going to use. Further on, if you have access to better manufacturing facilities like 3D printing or cardboard laser cutting, and you want to make the exact tools, then you make use of this website called Airfoil Tools. Now we'll just see how you can, design your own airfoil. Yes, it's not necessary that you need to take a pre-made up airfoil. You can experiment with different airfoil values, and let's see how you can do that. So basically, the two characteristic force coefficients which determine the behavior or properties of an airfoil are the lift and drag coefficients. Okay, so the lift and so the lift and drag coefficients are the ones which describe the property of these airfoils. So basically, why do we use these coefficients? Because every different, like for example, if you have the same airfoil shape, right? If you have a longer wing, if you have a broader wing, if you have a bigger wing, the lift force is going to change. But the force coefficient is defined in such a manner that it is characteristic to that shape of the airfoil, irrespective of its dimensions. So, however big or small, like however, if you want to enlarge the shape, if you want to crunch down the shape, it's up to you. But that specific shape of the airfoil or that specific contour of the airfoil is going to have that fixed lift coefficient. Okay. And how is that lift coefficient defined? The lift coefficient is defined as 2 times L. Small l is lift per unit length of the wing. Okay. And times divided by the density of the surrounding fluid, that is air in this case, square of the free stream velocity times the chord length. Okay. Similarly, the drag coefficient is defined as 2 times the drag force per unit length, and it is going to be rho v square divided by c. Then there are different moment coefficients such as pitching, rolling, yawing. Pitching is the most important one. You can explore about these coefficients in detail later. Basically, the most important thing that you need to mention, that you need to have is that the pitching, the CM curve, it is called CM. So it's called CM. And the CM versus alpha curve should have a negative slope. For this should have a negative slope if you want to make a stable fixed wing aircraft. Why? It's up to you. If you're not an aerospace and mechanical engineering student, you probably don't know. Just go and look it up. If you are an aerospace and or mechanical engineering student and you don't know, then it's bad. It's really bad. You should know that fixed wing aircrafts should have a negative CM versus alpha slope. So for it to provide stability. Then Basically, how do we name these airfoils? So the airfoils are named using this standard procedure called, so this is a NACA 4-digit series airfoil or NACA XXX. There are 5-digit series, 6-digit series. Those are much advanced airfoils. You will not require the knowledge of those airfoils until unless you are working in industry or working on a very specific project. If you're working with RC aircrafts, even if you have like high-end access to 3D printing or laser cutting for making your fuselage and airfoils, then just stick with NACA 4-digit nomenclature. So how do you like, how does this nomenclature decide what kind of airfoil you're going to have? So the first digit tells you that what is the maximum camber as a percentage of the chord length. The second digit tells you the distance of the maximum camber from the leading edge in tenths of the chord. And the last two digits basically tell you the maximum thickness of the airfoil as a percentage of chord change. So here I have taken a screenshot of the airfoil tools website where I just plotted a NACA 0012 airfoil. So just let's do a short demo of how this works. Just go and click on NACA 4-digit airfoil generator. So you already have a NACA 2412 airfoil by default. So as you can see, the first airfoil, yeah. So if we have a close-up look, then the first digit is going to be from 0 to 9.5%. It tells you the maximum camber. Then you put 4 to 4, so that's the maximum camber position. And I told you it was in tenths of the chord. So it's 40% of the chord length. So at 40% of the chord length, you are going to get maximum camber, and the maximum camber is 2% of the chord length. So basically, the the mean reference line of the geometric center line of the airfoil is bent, and it is maximum, like the point furthest away on this from the chord is 2% times the chord length, 2% of the chord length. And the thickness is going to be 12%. So um, it's basically telling you how much thick the airfoil is going to be. That we talk about wing shape and size. So we are understanding like airfoils. So how do you interpret all of this lift and drag coefficient data? So basically, let's focus on every curve one by one. So this alpha is the angle of attack. If you have forgotten, then I'll just review that slide because a lot of you are not from the aerospace background. Yeah. So this angle is alpha, right? And what is this angle? This angle is the angle between the reference line of the fuselage and the flight path vector or the free stream velocity. This angle is okay. Do not think that you're always flying in the direction of the nose of the aircraft. People have this misconception, like this horrible misconception. A lot of people who are like, even though they are students of aerospace, and the people who are not the students of aerospace or have not studied flight dynamics, don't think that your aircraft's velocity vector is always coming out of the aircraft's nose. Just because the aircraft has a pointy nose, that does not mean it's a direction of in what direction the aircraft is going. The aircraft can go in a different direction and its nose can point in another direction. So the if you think the fuselage reference line will more or less pass through the nose, let's say it's not necessary, but let's say it's passing through the tip of the nose, then the angle that the nose makes with the movement of direction is going to be the angle of attack. Okay, that's called AOA. So now let's move back. So this is CL versus alpha curve, and this is going to be this is it's a CL versus alpha curve for NACA 0012. So as you can see, an important thing to notice is that there is CL on the, so this is obviously CL on this and alpha on this. So if you look at 0 degrees, we have zero lift. So if the airfoil is exactly, like for example, if the airfoil is rightly aligned with the flight path vector, then there is zero lift. Okay. As you increase the angle of attack, right? As you increase the angle of attack, for example, like this, then there has to be an angle of attack between this is the flight path vector and this is the airfoil. Then only there is lift. This is the case for symmetric airfoils. So if you, okay, so this is the case for symmetrical airfoil, because what is going to happen if the airfoil is symmetric and it's at zero angle of attack, it is the flow on the top of the airfoil and the flow at the bottom of the airfoil are going to be deflected equally. So the forces that the upper surface of the airfoil is experiencing and the forces that the lower surface is experiencing is going to be same. So the net lift is going to be zero. So you need to incline symmetric airfoils at different angle of attacks to get lift. However, that is not the case with asymmetric airfoils. For asymmetric airfoils, what you will see is that you will really get very nice lift at zero angle of attack, but these airfoils perform very badly at negative angles of attack. The symmetric airfoils don't perform very badly at negative angles of attack. The more or less the term symmetric also means that if you are varying them in positive and negative angles of attack, if you see this is the positive negative line, it's symmetrical. The behavior is symmetrical. It's only like in the opposite direction. It's exactly in the opposite direction. Okay. Similarly, the CD curve. Now CD is basically the drag curve. So if you are increasing your angle of attack, the drag is also going to increase because you are stopping more and more amount of flow. You're deviating more and more amount of flow. So your drag is also going to increase. Now comes the comparison CL versus CD. For which NACA airfoil are these results obtained? Oh, these are for NACA 0012, symmetrical airfoil. So yeah, I have generated these from airfoil tool itself. So you can just go back, go to airfoil tools, and you can just scroll down. So here you will find NACA 0012, click on it, and you will get all the details. And this is at Reynolds number 50,000. So I'm going to remove all the other results and I'm going to update the plots. You'll see that you'll get all the plots required for your airfoil. Does that clear your doubt? Yeah, great. So moving on, now comes the fact that, so now do you observe something interesting? As you are increasing the angle of attack, you are generating more lift. That's nice. But you're also generating more drag. That's bad. So what you're going to do is, uh, what you're going to now, what you're going to look at is a trade-off. How much drag can I take on for more lift? Like your drag is being countered by the motor that is spinning and producing the thrust. So if that cannot, that can spin only at some maximum RPM, and beyond that, it's not going to produce more thrust. So if it reaches the limit where drag is like almost going to overpower the thrust, it's not safe. Those flight conditions are not safe. You'll suddenly have a reduction in your flight velocity. Suddenly the drag will overcome and your flight velocity will start reducing. And then when your flight velocity reduces, your drag reduces, then what happens? So basically this oscillatory behavior will come into play. Try to follow what I'm saying. It's going to be a bit confusing. So if you get like phased out or zoned out, just stop me or put it in the chat. So if you have, I'll just draw it a little better for you to understand. So if you have an aircraft, the motor is providing it a thrust in the front and there is drag. So if you are increasing the angle of attack, the drag is increasing. If the drag becomes greater than thrust, then what will happen? The velocity of the aircraft will reduce. But because drag is dependent on the velocity, it's a direct function of velocity, the drag will also reduce momentarily. Okay? Then momentarily, because thrust is greater than drag, what is going to happen? The velocity is going to increase, which will again increase the drag. So this oscillatory behavior will keep on happening, which is not something good. It is going to make the aircraft unstable. So, there is a limit to which you are going to increase your angle of attack. Also, on another factor, another note, if you notice something with respect to the CL versus alpha curve, you see the lift coefficient is goes to a maximum of about 0.75 or 0.78 angle at an angle of attack of roughly 7 degrees. After that, the lift starts to come down. So this is called stall. If you want to study what happens exactly in stall, you can go and explore it out on your own. But it's basically to understand it more, to just to give you an intuition of what is happening, is there is going to be an inclined airfoil like this, and I'll just copy the same airfoil, but this time I'm going to tilt it. Okay, and this is the oncoming flow. Now, after the flow has deviated from the aircraft, it needs to meet back here, right? For the whole deviation to be complete and for the flow to remain stable, or, but what happens is when you have such high angles of attack, this flow gets slowed down so much. There is also friction in real life. Potential flow theory assumes there is no friction, but practically there is friction. It slows down, and then there is a adverse pressure gradient from on the upper surface, which makes this flow curl up, and it never crosses the trailing edge. And this leads to loss of lift. This is called stall. So if you go beyond an angle of attack, like higher than a certain angle of attack, you are going to lose lift, and that is called stall. So you need to understand that there is only a maximum point or a maximum angle of attack that your aircraft can fly to. After that, it will lose lift. You just can't keep on increasing the angle of attack and expect that the lift will keep on increasing. Okay. Finally, the pitching moment again. I told you that the pitching moment curve is very erratic, but again, we look at this section where we want the curve to be negative. Okay. Wing shapes and sizes. So finally, making a final comment on what wing and shape and size. You want your main wing, the wing that is going to generate most of the lift, to be asymmetric, so that even if you are flying at zero angle of attack, you have nice lift. The control surfaces, the ailerons, the elevator, the rudder that we'll discuss about later, should be symmetric in nature, because they're going to go up and down, and their effectiveness in going up and down should be similar. That is why they should be symmetric. Now, what kind of airfoil do you want for a specific purpose? So if you're making surveillance drones, then you need, like, it is going to simply fly in one position for for all of the time. So it's just going to have a steady level flight. So you want an aircraft which has low drag at zero angle of attack, so that your motor is not going to expend a lot of energy in countering drag. However, if you are making racing or acrobatic drones, they are going to make sudden shifts in their orientation. They are going to climb up, go down. So here the important fact is that even if I go to a higher angle of attack, I should not lose my lift. So I should look for airfoils which provide me lift even at very higher angles of attack. Okay. So your different drone is going to pose different requirements of what kind of airfoil you want to make. Also, all of the curves that I have shown you here is at 50,000 Reynolds number, right? These curves change, the CL and CD values change, the CM, the pitching moment values change at different Reynolds numbers. So if you have a different, like if you want your aircraft to go at a different velocity where a Reynolds number is coming out to be different. So for example, I'll just do a sample calculation to verify 0.225 into 15 square into the part length is 0.2 divided by 0.001. Yeah, so the Reynolds number range that is applicable for RC aircrafts is probably around for these aircrafts as well. It lies somewhere between um, 10,000 to 50,000. And if you're going higher velocities for bigger RC aircraft, it can go up to 1 lakh also. So these aircrafts are very useful. Like, yeah, the airflow plotter is going to give you different results for different aircrafts. And if you want just an ending note to this section, if you want much more accurate results with respect to lift and drag, then you need to go into CFD analysis. And that is something really advanced, and that is beyond the scope of this workshop. So I'll take a small break. Um, and if anyone wants to interact or ask a question, if they have some ideas to discuss, this is your time. Okay, I guess we have no questions or doubts. Okay, we'll move forward. So now I'll quickly cover three sections, which are fuselage, empennage, and control surfaces. And then we'll go on to a demo of the aircraft. Okay. Why there is a negative lift after the zero? Yeah, so basically what is happening is this curve, like it's basically going to be, so you are going to have to see the change of flow field. It's basically, it's transient, it's more or less transient, it's not a permanent effect. The small change in angle of attack that you are seeing, the small negative lift that you are seeing at lower angles of attack is basically you'll have to go into the nitty gritties of the pressure distribution, but more or less it settles to a zero or positive lift coefficient after a while. Also, like, you'll see that these graphs like differ when you change the Reynolds number. If you look at lower Reynolds number flights, it is going to be absolutely positive. So basically what is happening is, as you increase the Reynolds number, some effects come into play, which exactly do not keep it laminar anymore. I could say that a transition region happens, other effects come into play. However, it is not important for RC aircrafts. Okay, so I guess there are no more doubts or questions. So we'll move ahead with the fuselage part of the RC aircrafts. So now everything that I tell you is a thumb rule. Okay, it's based on experience, it's based on reading, and it's based on like experience of other people's who have been making RC aircrafts. So if you want to make a fixed wing RC aircraft, you divide the fuselage into three parts. So basically, this is the whole fuselage length from the nose to the end of the tail. Okay. And you can divide the whole fuselage into three sections. So this is the leading edge of the main wing. So as you can see, leading edge MW means main wing. Okay. And leading edge HS means leading edge of the horizontal stabilizer. This part is called the horizontal stabilizer. I'll just give you a more clearer view. So this part is the horizontal stabilizer. Oh, sorry. Pardon me. That was wrong. This part is the horizontal stabilizer. I'm very sorry for the mistake. So the first part of the fuselage F1 from nose to the leading edge of the main wing. Then there is the chord length. Okay. And then there is from the trailing edge of the main wing to the leading edge of the horizontal stabilizer. And then there is the length of the horizontal stabilizer. These three parts, four parts make the whole fuselage length. Now, how do you determine? So after you have chosen your wing shape, you know how much payload you are going to carry. You know the lift coefficient, you know the cruise velocity. Now you know how much wing area you need, right? And you, since like you can decide that for the, like you can take a calculated guess for your chord length and you can get the wingspan. So once you have the whole wing portion ready, the wings, we'll do all these calculations in detail tomorrow interactively. Don't worry about it. So once you have the wingspan completely ready, so the fuselage is going to be 75 to 85% of the wingspan. Then from like F1, from nose to the leading edge of the main wing, it's going to be 15 to 20% of the whole fuselage length. So you get the fuselage length from the wingspan, you get the first part of the fuselage length from the full fuselage length, then you get F2 as 30 to 40% of F. So this is 30 to 40% of F. And then F3 is obviously the full fuselage length minus F1 minus F2 minus the chord length. Okay. So this is going to be your whole fuselage length. Now, how thick and how wide, like how, what should be the height of your fuselage? So your fuselage is going to be something like this, or it's going to be something like this, or it's going to be a completely spherical thing. It's up to you. So what is, yeah, okay. Sorry, I thought that someone asked a question. So basically, how do you find out like what height or width should you keep? If you are making an RC craft for the first time, just keep it square. Okay. Now, what is important is this ratio, fineness ratio. Fineness ratio is basically the length of the fuselage divided by the maximum width. Okay. Can anyone just tell me that what is the fineness ratio actually telling us? Like a very simple intuition. Like the whole, so I'll just draw it out for you so that you have a better understanding. So this is the length of the fuselage and this is the width of the fuselage. We're taking a square section. So this ratio, length by width, what do you think it is telling us? So if you have an intuition, you will understand that this is telling us how sleek or how slender our fuselage is. Okay. So basically what is happening, to give you an intuition, understand this very nicely. This intuition is very important when you are designing a fuselage. So this length L is going to be the distance where the fluid is parallelly flowing to the fuselage. So the fluid does not have any problem with the fuselage, as in the fuselage is not blocking the flow. But this dimension W, this is the area that the fuselage is blocking. So the fuselage is also contributing to lift and drag. Okay. Now The lift portion is very nominal or poor, but the drag is noticeable. If the fuselage is symmetric, the lift is almost zero. However, the fuselage is generally not symmetric and there is some lift associated. But you see, the fuselage contributes to drag. It's noticeable. So if you make it more slender, it is going to be much more streamlined and it is going to produce less drag. So that is why we want this fineness ratio. Okay, so I have made a mistake in my presentation. I just realized this. So this fineness ratio is not going to be in the 0.1 to 0.15 range. This fineness ratio should be in the range of 10 to 15. I made a mistake. So your fuselage length should be 10 to 15 times of your maximum width. Okay. So make it a slender, sleek, slender body. The higher the fineness ratio, the more sleek or slender your body is going to be, and the lesser drag it is going to produce. Okay. However, there is another problem. If you increase the length too much, so higher fineness ratio is going to give you lower drag. That's true. But if you increase the length, what is going to happen? You are basically controlling the pitch of the aircraft. So you have elevators at the back and you have rudders at the back, right? The elevators control pitch and the rudders control yaw and to some extent roll also. So now this is the CG, which is roughly going to be near the wing. And if this length is too much, then even a small force by this rudder or elevator is going to produce a huge moment. So it is going to become very sensitive. So you again have to do a trade-off. So everything in aircraft design is a trade-off. You have to understand that everything is a trade-off. You have to sacrifice something for something else, and there is no one single solution to, okay, this is the perfect value. You can never say that this is the perfect value in aircraft design. This is the best value or this is the best thing we can do. So again, you need a higher finesse ratio. Generally, fixed wing aircrafts have higher finesse ratio because we want the fuselage to be as streamlined as possible. And then basically, what do you say? And then we have, it increases the sensitivity of control surfaces on the empennage if it's too long, right? So we have problems here. So we need to, accommodate both the factors into play. Then comes empennage. Empennage is a fancy term for tail section. Okay, but I specifically mentioned the title as empennage because anyone who has been through workshops should at least basically be, familiar with the basic lingo that is used in RC design or aircraft design. So this section is called empennage, the end of the aircraft or the tail section of the aircraft. And this portion, this part, so you can see it's already labeled. This is the horizontal stabilizer. Okay. Why is it called the horizontal stabilizer? Can any um, aerospace engineering student here, would they like to discuss if they are willing to? Okay. So basically, I told you earlier that, we are looking for a negative CM or CM versus alpha curve for the whole aircraft, not just for the wing, for the whole aircraft. So what is happening if you're trying to pitch the aircraft upwards, right? The aerodynamic center will keep moving forward and backwards. Okay. So when you pitch the aircraft up, the aerodynamic center will move forward in the wing. So what is going to happen is it might happen that, the aerodynamic center crosses the CG and it creates a, a rolling moment which pushes the aircraft upward. Okay. But then you have this horizontal stabilizer at the back, which can help you in bringing it back down. So that is why it calls a horizontal stabilizer. Similarly, the vertical stabilizer helps in keeping the aircraft stable in the yaw and roll direction. Okay. So how do you design these? So let me just write this down, because otherwise you'll not be able to relate. So if you remember, we had found out F3. F3 is nothing else but the length of the horizontal stabilizer. So we already have the length of the horizontal stabilizer. This is F3. Okay. For making a beginner RC aircraft, making a square or rectangle horizontal stabilizer is absolutely fine. When you foray into advanced RC aircrafts, you can understand how sweep and taper improves the performance. But right now, we know F3, and the thumb rule is that the area of the horizontal stabilizer should be 15 to 20% of the wing area. So now you know the area, so you can determine the length of the horizontal stabilizer by dividing F3, by dividing the area of the horizontal stabilizer by F3. And finally, you know the vertical stabilizer. Now the area of the vertical stabilizer should roughly be 33% to 40% of the horizontal stabilizer area. And as a thumb rule, again, as a thumb rule, what is going to happen is the width of this vertical stabilizer is going to be roughly the same as the width of the horizontal stabilizer. So you can find out the height of the vertical stabilizer by dividing the approximate area of the vertical stabilizer by the F3 value. Okay. Moving on to control surfaces, these are the standard values that you can use for designing ailerons, elevators, and rudders. I am not going to go over the values in detail, but yeah, looking at this picture is important, because so again, I told you now this is a great diagram to tell you about the body frame axis. So let's say this is where the CG of the aircraft is. Okay. One axis. Sorry. One axis comes out front. Okay. This axis is parallel to the fuselage reference line. One axis goes on the starboard side. Okay. And one axis goes down. This is called the body frame. Okay. And this is the CG of the aircraft. The CP of the aircraft should somewhere be here. Sorry, the CP of the wings, not CP of the aircraft, the CP of the wings, the CP of the main wings. I should write it down. The CP of the main wing should somewhere be here. Okay. Is it clear to everybody? If anyone has any doubt in this diagram, please let me know right now. Okay, no doubt. Fine, great. So yeah, so this axis is called the x-axis, this axis is called the y-axis, and this is called the z-axis. And we denote it with small b. This is all flight dynamics terminology. Okay. So this is parallel. So this one is parallel to fuselage reference line. Sometimes some in special cases it may not be, but generally it is. So now what is going to happen? You see, I told you that if we look at the ailerons for a moment, okay, we'll have a side view. So let's say this is the wing, okay, and these are the ailerons. So right now, what is happening? The so to make it even more, um, let's make a quiz out of it. So I have um, broken airfoil into two parts. This is a symmetric airfoil. Okay. Now, what I do is I make the end part tilt downwards. So there is an axle here, and now the whole airfoil looks somewhat like this. So what do you think? Is it going to increase the lift or it is going to decrease the lift on the airfoil? Okay, so I have shared a poll with everyone. I think everyone should see it on the screens right now so that I can have a quick understanding of, do you guys understand what I'm trying to say or not? So I've just shown you a case here where there is a symmetric airfoil and I'm adding a small flap to its end and I put it downwards. Does it increase the lift? Does it decrease the lift? Or you are blissfully unaware of what is happening in the workshop? Okay, so it's been a minute and okay, enough of you are active. So yeah, other than a small misconception, the lift, other than two people having a small misconception, the lift is going to increase. Why? Because now the camber has become positive. The camber, I told you that asymmetric airfoils at zero angle of attack is going to give you positive lift. So now it is going to give you, now the lift is going to increase. So earlier there was zero lift, now the lift is going to increase. Now what happens in the case of a normal, or like in the case that we are dealing with here in this aircraft? So you already have this wing and this wing producing equal amounts of lift. We'll I'll just use a different color. I'll just call this lift on the starboard side and lift on the port side. Now, if you wanted your aircraft to turn this way, so if you are looking at me, then I don't know if my camera is mirrored or not, but this is my starboard side and this is my port side. So right hand side is the starboard side, left hand side is the port side. And when I'm flying like this, when both of my wings are exactly symmetrical, both of my wings like are symmetrical in arrangement, then I am producing equal amount of lift on both the wings. So I am stable, right? Now what happens when suddenly I tilt this aileron down? I turn this aileron down and this aileron up. Now this portion of the wing and this portion of the wing are going to produce lifts in opposite directions because this is up, right? If I look at its cross section, then it is going to look like this. So this will produce lift in this direction. And because this is down, its cross section is going to look like this. So it is going to produce lift in this direction. So what will happen in this scenario, the starboard side lift, the whole lift produced by the whole starboard side is going to decrease as compared to the port side, right? Which means that if I were to take a moment of these two lift forces, right? So if I were to take a moment, so let's say this is our starboard and this is our port, which I can say is roughly similar. So we can call them, so we have R star roughly equal to R port and we have R. So we take the moment L star into R and it is going to be in the opposite direction to the port side lift moment. So we are going to see that this moment is not zero. It's some non-zero value. So basically, I am experiencing a moment in this direction. So my aircraft is going to roll. So ailerons help in rolling. Also, the people who are in aerospace engineering and who want to have some advanced knowledge, let me tell you that not only affects rolling, it also affects yawing to some extent. For that, you need to have a very detailed understanding of how the flow physics is changing. But that effect for RC aircrafts, you can neglect it. For RC aircrafts, you can imagine that the rolling, yawing, and pitching are all independent of each other. Okay. Similarly, again, the rudder thing. Now we focus on the rudder. So right now the rudder is like this, all good. When I shift the rudder this side, then what is going to happen? The lift is going to become this side. So with respect to CG, there is a force in this direction. So what is going to happen? If I'm an aircraft like this and then apply a force at my tail like this, I am going to tilt like this. So the rudder is controlling yaw motion. The aileron is controlling roll motion. And finally, when we talk about elevators, if we tilt, so basically the elevators, they go down or up together. They don't go separately. Okay. So the elevators either go down or they go up, okay, together. So when the elevators go down, they produce a lift in this direction, which makes the nose go pitch down. So elevators down, nose pitch down. Elevators up, nose goes up. Okay. So these are the control surfaces which help you control a fixed wing RC aircraft. So now I think you have understood why it is much more difficult to control a fixed wing aircraft as compared to a rotor wing aircraft. Is this idea clear to everyone? That to understand the controls of a fixed wing aircraft, you need to have a good understanding of all the control surfaces. Does anyone have any doubt up till this point? I guess not. Okay. So now, since we are short on time, we'll do a swift overview of the power plants, and then tomorrow we'll take up the rest of the detailing on how do you choose a battery pack. But uh, basically, how does the power? So finally, how do you choose on the power plant of the aircraft? Okay. So basically, the power plant consists of battery, motors, ESC, and propellers. What is an ESC? ESC is nothing else called, it's called an electronic speed controller. Okay. So basically, the battery pack is going to power the motors and the electronic speed controller. The electronic speed controller is going to receive control signals from your manual transmitter or your autopilot. The electronic speed controller is going to feed signals into the motors, and it is going to run the propellers, which is in turn going to produce thrust and make the aircraft go forward. Now, in tomorrow's discussion, we'll talk about how to choose battery packs and how to choose the motor, how to choose the propeller, how to choose the ESC. And then we'll talk about manual control and we'll talk about automatic control shortly. So now I'll just attach my phone and give you a tour of the RC aircraft. Okay. You guys can unmute yourselves if you want to. In this case, I'll just give everyone permission to unmute yourselves if you want to ask anything. Let me just start with it. And Okay, so I am going to switch off. So I'm going to switch off my video here. Are you guys able to hear me? Can someone just put down a confirmation? Yes. Okay. So if you guys want to unmute yourselves and ask a question, you can ask it. You can just, give me a pop-up that you want to, unmute yourself, and I'll just give you the permission to unmute yourself. So I'll just take you on a virtual tour of the aircraft since we can't do this in person. So yeah, I guess I'll just pin my video so that I can see it here. So as you can see, um, so this is the RC aircraft, and some of the tips that I would want to give you if you want to make a note right now is if you're making an RC drone, you need to use light materials. So what are the options you have to make these materials? You have the option like you can use sunboard, MDF boards, or Depron sheet foam, or Depron foam sheets, or balsa wood. Like I would really like you to note down if you are going to work on RC aircrafts in the future. Then, like the materials that you're going to use is sunboard, MDF board, Depron foam sheets, or Depron sheets, or basically, yeah, MDF boards. Right. Then, as you can see, this is the fuselage nose. I have mounted the motor here. We'll be talking about motors and propellers in more detail tomorrow. This is the battery charger. Right now, the battery is under charging. So these are the control surfaces that you are seeing. So as you can see, here is a servo motor, and these are the. So if I don't know if I can tilt this. Yeah, it's not powered right now. So if I take it down, so basically right now what is going to happen is the lift on this wing is going to get reduced, and this side of the wing will tilt down. If you push it down, the lift on this wing is going to increase, and this side of the wing will go up. That's how you control the ailerons. And further down the line, you have the horizontal stabilizer at the end. I'll just point to it. So this is the horizontal stabilizer. This is the vertical stabilizer, and this is the rudder attached to it. This is the servo controlling the rudder. This is the servo controlling the elevators. So we'll see how to control each of these using manual control tomorrow. And we'll also see why we made the choice for this motor and why we have a certain battery pack here. And this is the electronic speed controller. So we'll learn more about this in detail tomorrow. And if anyone has any questions for today, then I would like to take them up. I guess no one has questions for today. So we'll call off the meeting and you'll all get a link for tomorrow's meeting in your mail, either tonight or by tomorrow morning. So thank you for being with me. See you tomorrow.